Chapter 15 will primarily focus on equilibria of slightly soluble salts. You might remember in General Chemistry 1, we learned some basic solubility rules for ionic compounds in water. Typically soluble compounds were alkali metals of group 1A, salts that contained the ammonium ion, nitrate ion, perchlorate, chlorate, or acetate. Chlorides, bromides, and iodides are typically soluble unless they were with silver, lead 2+, or mercury. And sulfates were soluble except with lead, calcium, strontium, mercury, and barium. There was some solubility rules for which compounds were typically insoluble as well. We learned that normally hydroxides and metal oxides are insoluble, except if they were paired with a group 1A metal or calcium, strontium, or barium. And we learned that phosphates, carbonates, sulfites, and sulfides were typically insoluble unless they were with a group 1A cation or the ammonium ion. We're going to see in this chapter that the rules that we learned for compounds that were typically insoluble were just kind of basic rules, and those salts will actually dissolve in water to a very, very small extent. So we call them slightly soluble solids or sparingly soluble. Let's imagine that we mix together two solutions, one of silver nitrate with sodium chloride. We could write a double replacement reaction to predict our products. We would form sodium nitrate, which is NaNO3, and we would also form silver chloride. Using our solubility rules, the sodium nitrate, we would put an aqueous after that because we would determine that that substance is going to end up being soluble in water. The solubility rules would tell us that something like silver chloride would end up being insoluble and would get a subscript S after it, indicating that this should be solid. Now, what we're going to talk about in this chapter is that even though that silver chloride is a solid and it's mostly insoluble, they're not actually 100% insoluble. So some of that silver chloride will dissociate and break up into its respective ions, which are going to be the silver plus ion and the chloride anion. We would look at the subscripts that are in the formula of the salt to determine how many ions it breaks up to when it dissociates. So since there's a 1 here and a 1 here that's unwritten, we would get 1 mole of silver ions for every 1 mole of silver chloride, and we would get 1 mole of chloride anions for every 1 mole of silver chloride. So everything in this equation is 1 to 1 to 1. Now there is an equilibrium that will be established between the dissolution of the solid and the precipitation of the silver ions and the chloride ions going back to form a solid in a perfectly saturated solution. So once again, we're looking at double arrows for these slightly soluble salts that we're going to use, so it's an equilibrium that's established, which is what will make this familiar to the previous chapters we were doing, is that we're still just dealing with a different type of equilibria taking place. From our equation of our slightly soluble salt dissociating into its ions, we could write our equilibrium expression. Our equilibrium expression is going to be the concentration of the products over the concentration of the reactants raised to the powers of the coefficients from the balanced equation. The only thing that's going to change in this chapter is, since we're dealing with salts that are sparingly soluble, they are solids. And recall that we don't include solids or pure liquids in our equilibrium expression. So essentially, we're never going to have a denominator. We would have K equal to the concentration of silver ions times the concentration of chloride ions, and that whole thing would be over 1. K is now referred to as KSP. SP stands for the solubility product. So KSP is called the solubility product constant. Just like all of the other K values that we've looked at, it's measured experimentally. The right side of our equilibrium expression is referred to as the ion product now, because we have no denominator, so we're taking a product of the concentration of those two ion components. There will be not very many ions in solution because these salts are only slightly soluble, so the equilibrium for them will lie far to the left. It'll lie mostly to the side of the solid. When comparing the KSP values, the larger the KSP is, or the magnitude of the KSP, that means that that substance or that salt is more soluble. We have a chart of KSP values online that you can look at, and it gives you them for a variety of different slightly soluble salts. You're going to want to keep that chart out by you while you're doing problems in this chapter. Write the chemical equation and KSP expression for the dissolution of the following slightly soluble salts. A, we have lead 2 fluoride. If we were to use our solubility rules, we would see that lead 2 fluoride should be assigned as a solid. It's insoluble. But now we know that it's going to be slightly soluble. So when we write our equation for the dissolution of it, we're going to use double arrows because there will be an equilibrium established. And it's going to break up into lead 2 plus ions, which will be aqueous, plus we're going to get 2 moles of fluoride anions, which will also be aqueous. The 2 moles of the fluoride anions come from the fact that in our formula for lead 2 fluoride, we have a 2 there written for our subscript. So when those combine, 2 fluorides always combine with 1 lead 2 plus ion. Writing our KSP or our equilibrium expression, we're going to have KSP equals the concentration of lead 2 plus ions times the concentration of fluoride anions, and we have to square the fluoride concentration because we have a 2 out in front of it in the chemical equation. Next, B, we have iron 3 hydroxide. According to our solubility rules, iron 3 hydroxide would be a solid, and so it's going to dissociate in solution a small extent, and it would break up into iron 3 ions, and we would get 3 moles of hydroxide anions. And once again, that 3 out in front of the hydroxide comes from the fact that there's a subscript of 3 after the hydroxide in the formula for the salt. Our equilibrium expression would be KSP equals concentration of lead 3 plus ions times the concentration of hydroxide ions, and we have to cube our concentration of hydroxide ions because we have a 3 out in front of it. So remember, if you have a 2 out in front of something, you square it. If you have a 3 out in front of it, you would cube it, so on and so forth. The next important thing to define is something called the molar solubility. But first, I want to remind you what a saturated solution is. A saturated solution is a solution that specifically has the maximum concentration of solute dissolved in the solvent. Essentially, it will not allow any more solute to be dissolved at that point. And if it had less solute dissolved, it would actually be unsaturated. So it has that perfect maximum amount of solute contained within the solvent. A saturated solution is important because it's a solution that's at equilibrium, where the rate of dissolution of the salt is perfectly equal to the rate of precipitation of the ions coming back together and reforming the solid. When we talk about the molar solubility of a solution, it's the number of moles of solute dissolved in exactly 1 liter of a saturated solution. So there's that restriction on it that the solution is saturated when we're referring to the molar solubility. So moles of solute dissolved in 1 liter of a saturated solution. Let's imagine we have a saturated solution of calcium fluoride. What would that look like? Calcium fluoride has the formula CaF2. And according to our solubility rules, this should be a slightly soluble solid. So it would break up into its respective ions, and it would form the calcium 2 plus ion and 2 moles of fluoride anions. The ions would be aqueous, meaning the ions are swimming around in the solvent, but the solid portion, the undissolved calcium fluoride, would not. That would be separated out from the solvent as a precipitate. So that's what we can see in the picture on the right, is that we have our solid calcium fluoride sitting on the bottom, and then we have a certain ratio of ions that are swimming around in our solution. Notice that there are, in this example, 3 moles of calcium 2 plus ions, and then there are double that amount of fluoride anions. So in the picture, you can see that there are 6 moles of fluoride anions. So there's always going to be that 2-to-1 ratio of fluoride to calcium just because of the chemical formula of the solid itself. We could next write the KSP for our equation. It would be equal to the concentration of calcium 2 plus ions times the concentration of fluoride anions, and we would have to square our concentration of fluoride anions because we don't want to forget that we have that 2 out in front of it. In this chemical equation, we can see that our ratio for the solid calcium fluoride is 1-to-1 with the calcium ions, but it's 1-to-2 with the fluoride anions. And the calcium ions to the fluoride ion concentration are also 1-to-2. So what that means is our concentration of calcium ions would be the same as the concentration or the molar solubility of our calcium fluoride, but our fluoride anions are going to be 2 times the amount of our calcium ions, or 2 times the concentration of our calcium fluoride as well. Let's try an example where we calculate the solubility product constant, or the KSP, from a given molar solubility. Silver bromide has a molar solubility of 7.1 times 10 to the negative 7th moles per liter at 25 degrees Celsius. What is the KSP value? So first we want to write our equation for the dissociation of our slightly soluble solid, which is going to be the silver bromide. Silver bromide's chemical formula is AgBr, and that's going to be our solid. It'll dissociate slightly and break up into its respective ions, which will be aqueous silver plus ions and aqueous bromide anions. Our equilibrium expression for this would end up being KSP is equal to the concentration of silver ions times the concentration of bromide anions. And remember that we don't have anything in the denominator because the left-hand side of our equation is a solid, so that doesn't get included in our equilibrium expression. Now, we were given in the problem the molar solubility of the silver chloride. It was 7.1 times 10 to the negative 7th moles per liter. So that's for the AgBr. But we can use the ratio or the stoichiometry from the balanced equation to figure out what the concentration of our ions are in solution as well. Silver bromide has a 1-to-1 ratio with silver ions and bromide anions. So their concentrations are also going to be 7.1 times 10 to the negative 7th molar, because they have that same 1-to-1 concentration. So we can use those concentrations in our equilibrium expression by substituting them in and then calculating the KSP. So our KSP will be equal to 7.1 times 10 to the negative 7th times 7.1 times 10 to the negative 7th. And that gives us a value of 5.0 times 10 to the negative 13th. Just like other K values, KSPs are reported without units. Let's try another example. Calculate the KSP for lead 2 fluoride if the molar solubility is 3.0 times 10 to the negative 4th moles per liter. Starting off, we're going to write our chemical formula for lead 2 fluoride. That'll be PbF2, and that's our solid substance. That's going to dissociate to a small extent into lead 2 plus ions that are aqueous, and we'll get 2 moles of fluoride anions. Whenever a molar solubility is reported, that molar solubility is for the solid, so that value is for the lead 2 fluoride. We can use our stoichiometry from our balanced equation to figure out what the concentration is of our ions in solution. We have 1 mole of lead 2 fluoride to 1 mole of lead to every 2 moles of fluoride ions. So we have 3.0 times 10 to the negative 4th molar for the lead 2 fluoride. We have 3.0 times 10 to the negative 4th molar for the lead 2 plus ion. And we have 2 times 3.0 times 10 to the negative 4th molar for our fluoride anions. So the fluoride concentration in this solution will actually be 6.0 times 10 to the negative 4th molar, 2 times the amount of the molar solubility. Next, we want to write our equilibrium expression. For this reaction, we're going to have KSP is equal to lead 2 plus concentration times fluoride ion concentration, but we still have to square the fluoride ion concentration. It's squared because there's a 2 out in front of it in the balanced equation, and the equilibrium expression is defined as the ratio of products over reactants raised to the coefficients from the balanced equation. So even though we multiplied the molar solubility by 2 to get the concentration, we still have to remember to square that term in the equilibrium expression. Plugging in our values, KSP will equal 3.0 times 10 to the negative 4th for the lead ions times 6.0 times 10 to the negative 4th molar for the fluoride ions, and that'll be squared. That gives us a KSP value equal to 1.1 times 10 to the negative 10th. You might notice when you look on your KSP chart in your notes that sometimes the KSPs you calculate in the problems are a little bit different than the KSPs on the chart. The values kind of vary from many different sources, so don't worry about that too much if they don't line up exactly. Usually the power of 10 will be the same, but the digits out front might be a little bit different. A saturated solution of lead 2 chloride at 20 degrees C was found to contain 4.50 grams of lead 2 chloride per liter of solution. Determine the KSP for lead 2 chloride. In this problem, we weren't given the molar solubility directly, but we were told some information that will allow us to calculate the molar solubility of our lead 2 chloride. Starting off with our 4.50 grams of the lead 2 chloride per liter, we can convert that into the molar solubility by converting the grams of lead 2 chloride into moles of lead 2 chloride. 1 mole of lead 2 chloride is equal to 278 grams. This way our grams will cancel and we'll be left with moles per liter. This gives us 0.0162 moles per liter of our lead 2 chloride. This is our molar solubility. Because our solution is a perfect saturated solution, that's how many moles of that salt will dissolve per liter. Next, we can write our equation for our salt, breaking up into its ions. So solid lead 2 chloride will dissociate slightly into lead 2 plus ions and 2 moles of chloride anions. From our molar solubility, we can figure out what the concentrations of those ions in solution will be. Our lead 2 chloride has a molar solubility of 0.0162 molar, and the lead ion concentration will be the same as the molar solubility, 0.0162 molar, because those two have a 1-to-1 ratio between them in the balanced chemical equation. The concentration for the chloride anions will be 2 times the molar solubility, so 2 times 0.0162, which gives us a concentration of 0.032 molar for our chloride anions. That's because we have that coefficient of 2 out in front of our chloride, so the stoichiometry tells us that there will be 2 moles of chloride formed per every 1 mole of lead 2 chloride that dissociates. Next, we want to write our equilibrium expression. That'll be the KSP is equal to the concentration of lead 2 plus ions times the concentration of chloride anions squared. From here, we can substitute in our concentrations. The lead ions will be 0.0162 molar. The chloride anions will be 0.032 molar, and that'll be squared. This gives us a KSP for lead 2 chloride of 1.6 times 10 to the negative fifth. The other thing that we can do is we can calculate the molar solubility of a slightly soluble salt from a known KSP value. What is the molar solubility of silver chloride in pure water at 298 Kelvin? Starting with writing our equation for silver chloride dissociating into its ions, solid silver chloride will break up into aqueous silver ions and aqueous chloride ions. We can look up what the KSP of solid silver chloride is off of our KSP chart. Our equilibrium expression would be KSP equals the concentration of silver ions times the concentration of chloride anions. The KSP for silver chloride is 1.8 times 10 to the negative 10th. All of the KSPs on your chart are going to be very small. They're very small because the position of equilibrium lies far to the left. Not very much of these salts actually dissociate into their ions. We can then solve for what our molar solubility is of our silver chloride by using the fact that we know the stoichiometry in this balanced equation. Everything is 1 to 1 to 1. So our unknown in this case that we can solve for can be the concentration of the silver ions or the concentration of the chloride ions, which would actually be the same as the molar solubility of our solid silver chloride. So when we don't know what something is, we call it X. So we'll call our silver ion concentration X and our chloride ion concentration X. Then to solve this, we have our KSP, 1.8 times 10 to the negative 10th is equal to X squared. And we can square root both sides of our equation to solve for just what X is. So X is equal to our concentration of silver ions in solution. It's equal to our concentration of chloride ions in solution. And it's also equal to our molar solubility. It comes out to being 1.3 times 10 to the negative fifth moles per liter. Let's try another example. Determine the molar solubility of silver carbonate in water at 25 degrees Celsius. Silver carbonate is Ag2CO3. That's going to be our solid salt. It'll break up into 2 moles of aqueous silver ions and 1 mole of aqueous carbonate anions. Next, we want to write our equilibrium expression. KSP will equal the concentration of silver ions, and we have to square that, times the concentration of carbonate ions. Next, we look up what the KSP is off of our chart for silver carbonate. You'll see that it is 8.1 times 10 to the negative 12th. Once again, we're going to use the stoichiometry in our equation to work backwards to figure out what the molar solubility of our silver carbonate is. So we have a 1 to 2 to 1 ratio in our balanced equation. That stoichiometry will tell us what we need to assign as being X. It's easiest to call just X the species that has a 1 out in front, and then we can say 2X, 3X, etc. for the other species. So our KSP we have plugged in. The silver, we would plug 2X into there, and it would be 2X squared. We still have to square that 2X times the carbonate, which would just be X. Then we can say the KSP, 8.1 times 10 to the negative 12, is equal to 2X squared, which becomes 4X squared times X. So really that comes out to being 4X cubed that we have equal to our KSP at this point. So we've got to actually take our KSP value and divide by 4 to get our x cubed alone. So we'll divide both sides of our equation by 4. That gives us x cubed is equal to 2.025 times 10 to the negative 12th. And then if we cube root both sides of the equation, that'll just give us x. And x is equal to the concentration of CO3 minus, because that's the species that has a coefficient of 1 out in front of it. And so it's also equal to our molar solubility for our silver carbonate. And x comes out to being 1.3 times 10 to the negative 4th molar.